So what we're going to talk about in this video, right, is how to kind of look at some of the data that exists, right, especially for the geometry optimization calculations that we probably want to pull out and kind of use to get an understanding of our molecule, but also to make figures and so forth, right? So once our computation is completed, right, we just click on this magnifying glass right here, and that'll pull up our data viewer. So what you're going to be greeted with is what your molecule looks like. So you can easily manipulate it and move it around. So there's, that arrow right there that lets you rotate it. If you have clicked the one that has like the arrows in all the different directions, right, that's the translation. So that way you can move it around left or right, up and down. And then there's also the magnifying glass, right, where if you click on it, you can zoom in, zoom out. And so, one thing that you really want to do, especially when you're looking at a molecule, is you always want to kind of have the orientation highlighting what you think is most important, right? So if we're looking at this THF molecule, a really interesting part to kind of look at is the fact that you have, carbons 1, 5, 4, and 3 all within the same plane, so to say, right? And then oxygen 2 is just kind of puckered out. And so if that's, a piece of data or something that you kind of want to highlight somebody to and kind of emphasize, making sure that you rotate everything so that way it looks that way is always going to be a good bet, right? So you kind of, get this rotated like this so that way you can kind of look at that part right there. Another thing that you may, be interested in, be like, okay, right, I'm kind of actually interested in the dihedral angle. So you would want to, let's say for like 1 and 5. So you can be like, okay, right, I have, these all lined up, right, this right here, right? So that way you have 1 and 5, you're looking down that axis and you're like, okay, right, this is what I'm most interested in, is, seeing like how much overlap is there between, hydrogen 13 and hydrogen 7, or hydrogen 6 and hydrogen 12, right? Thinking about where the orientations are always important when making any kind of figures. And one thing you can, think about too is like, you can always make a ton of figures in all these different orientations, and then when it comes time to writing your manuscript or when it comes time to presenting something, you can kind of then take that, those images and then present them, right? Essentially data storage is essentially not an issue anymore in this day and age. So you can, store as many as you want to in these cases, but you can always come back to it too, right? You don't necessarily have to do them all at once. You can just, come back to one WebMO and look at it. And so, if you want to then save one of the orientations, what you can then do is go here to File, and then here under Save Image, right, you can save it as either a PNG file or a POV-Ray file. So PNG, right, is just simply an image file. POV-Ray, you would then load that into like a ray tracing program such as POV-Ray, and then you can get a nice figure that way. But for most purposes that most people use it, PNG is pretty good in these cases. But you can also change the preferences, right? You click on Preferences, you can change the colors, the isosurfaces, various aspects of it, so that way it looks the way that you want it to look. Now, if we scroll down, right, all the different calculated qualities and quantities are all going to be available down here. So, looking here at just the general overview, it'll give us, the basis set that we had used. It'll also give us the final single point energy of our calculation. These are always going to be in Hartrees. And so you can just look up, right, what the relationship is between Hartrees and electron volts or joules or kilocals, right, depending on what you're interested in. Another thing, right, that gets computed is the dipole moment. And so here, right, we can see that the dipole moment of this molecule is 1.5254 dBs. And so that you have this little magnifying glass right here, right? And so the magnifying glass is always going to be just giving you an option to view what's going on. So if you click on it, right, what it does is it actually shows you on the molecule where your dipole moment is, right? So if that's the thing that you're most interested in visualizing, right, that's one thing that you can do there. Next, right, it's going to go through and it's going to show you how many steps it took to, optimize the geometry. And so here we can see it took 6 steps. If you wanted to, right, you can animate that. Another thing that we can look at are the overall partial charges on all the different atoms. So if you, look at the exact numbers, right, you can see what they're computed for all the different atoms. Another thing you can do is click on View, and it'll just simply show them on here. So that way you can see, which atoms have a negative charge, which have a positive charge. And hopefully, right, that kind of matches what you would probably expect based off of, the various concepts that you learned in organic chemistry in terms of, electronegativity of atoms, and then, valency and so forth, and how that all impacts it. Now, a really interesting and an important part, really, I think that you can get out of DFT calculations is looking at the molecular orbitals, right? So what we can do is, if we scroll down, right, we have, all these different options right here. We have orbital, symmetry, occupancy, spin, energy, and then actions as our different rows. And so orbital, right, is just simply the number of the orbital within the sequence. Symmetry doesn't really matter because Orca doesn't really use symmetry in the calculations. Occupancy tells us how many electrons are occupying that orbital. If it's one where it's a closed system, right, and everything was unrestricted, right, you're going to get a value of 2 here, right, because you would expect it to be 2 electrons in each one of them. Spin, again, that's not included for an unrestricted calculation, or sorry, for a restricted calculation, right, because all this electrons are paired up, so there's no, difference between, something that's spin up or spin down necessarily. And then here under energy, right, we can get what the energy is of that orbital that's calculated, and it's presented here in Hartrees. Now, one thing I want to point out, right, is that there's no reference value, right? They're all over the place, so there's no directly, 0 point. And so what you have to always do if you're going to be making any kind of like molecular orbital diagram that includes those energies is that you have to make that reference point yourself. A typical reference point that people use is going to be the HOMO, right, the highest occupied molecular orbital. People set that to 0, and then everything else can kind of get scaled from there. But what we can do too is we can look at what that highest occupied molecular orbital, right, what that even looks like. If we click here on the magnifying glass, and that'll pull it up, right? We can see here that the HOMO looks like this right here, right? Where you have, an anti-bonding interaction between the oxygen here, right? And the neighboring carbons in this case, right? Like a pi anti-bonding interaction. And then also still, bonding interactions between other atoms there as well. And then right here, right on this menu, you can click on all the different atoms. And so you can see what the different molecular orbitals look like. And then based off of that information, you can get a pretty good idea of, where, a nucleophile or an electrophile would necessarily want to attack on these atoms, right? Just based off of the occupancies and the types of atoms and molecular orbitals that you're looking at, right? So this is always good. And again, an important thing to do is, emphasize and orient the molecule in a way so that whatever it is that you're trying to emphasize for those molecular orbitals is possible, right? That you can see it in the figure that you're looking at. And so finally, right here all the way at the bottom, there's also additional things that have been calculated, right? You have your electron density, your electrostatic potential, right? The frontier density and so forth. And so, you click on these and, it'll calculate those properties based off of the information that we have. But here we can see, essentially, where, the positive region and the negative region and so forth are. And so that's, an important thing to do is kind of looking at a lot of these things, is making sure that the orientation is where you want it to be, but also making sure that the options that you're looking at, right, are the right options.